part of 2.4 today. I'll continue 2.4 on Wednesday, okay? But what I'm going to say here is the following to motivate this stuff, okay? When we have two equations and two unknowns, we know how to solve those, don't we? They might be a royal pain, but we do know how to solve them. We have our substitution method, and we also have our addition elimination method, okay? So when we have two equations and two unknowns, it's actually something that we can deal with in order to solve these things. You may or may not remember class on Friday, but on Friday, didn't we set up a word problem where we had 3 equations and 3 unknowns? Yes, we did, okay? And they get even bigger from there, okay? I've taken a real life example that had something like, 50 equations and 50 unknowns. Don't worry, I won't ask you to go there in this class. That's like way pushing it, okay? The most we'll have is either 3 equations and 3 unknowns or 4 equations and 4 unknowns. Now, there are techniques that you can use by hand to solve these. Maybe some of you have heard of the Gauss-Jordan elimination method. Okay? That's a method that you can use by hand to solve these things. Okay? Is it a hard method? No. Is it a pain? Totally. The reason why it's such a pain is if you make one tiny little mathematical error along the way, and everybody makes, computational error, you're done for the rest of the problem. Okay? So, the other reason why we don't really have to deal with it is because our calculators, using something called matrices, can actually take these things and solve them in a really sweet manner. Okay? So that's the way we're going to actually do this. So, our motivation for what we're going to be talking about today and Wednesday, maybe even into Friday, is just to solve bigger systems. Okay? So, I mentioned the term matrices, and the singular version is a matrix. Your plural version is matrices. Okay? Now, when we are dealing with matrices, we always name them. Okay? The names are not original. We name them with capital letters. Okay? Also, when we talk about a matrix, what we're particularly interested in is the size of the matrix. The size is how we distinguish what operations we can or cannot do. Now, it's usually some number by some other number. Your first number is the number of rows, and the second number is the number of columns. This is how we always talk about the size of our matrix. Okay? So, for example, I can have like my matrix A, and how about it's 1, 2, 3, 4, 5, 6. These numbers in here are called my entries. Okay? So, for example, this number 1, isn't he in my first row, first column? This number 5, isn't he in my second row, second column? So, what if I asked you, hey guys, what's the size of matrix A? Well, how many rows are there? 2. How many columns are there? 3. He's a 2 by 3 matrix. I know it's not that thrilling, but you have to be able to read the size of the matrix in order to enter it into your calculator. So, what if, on the other hand, I have this matrix? -1, 1, 2, -2, 3, -3. What size is matrix B? He's a 3 by 2, isn't he? Right? Because there's 3 rows and 2 columns. Do you want to know a really, I'll call him C for cute matrix? What size is he? He's a 2 by 2. Do you want to know why he's so cute? Of course you do. He's a square matrix. Whenever it's like 2 by 2, 3 by 3, 4 by 4, 5, 5, 5, you have the square matrix. We like square matrices. They're fun. Isn't he cute? All right. So, that is one quick comment. Now, I think you will grant me, and this isn't going to be relevant yet, but it's going to be relevant, I think, probably one of the first things we do on Wednesday. Two matrices are equal. This is a pretty intuitive thing to say. If they are the same size, and their corresponding entries are the same. That's a pretty not counterintuitive, that's a pretty intuitive definition, isn't it? Okay, if we're going to say that two matrices are equal, their sizes need to be the same, and their corresponding entries also need to be the same. Okay? You'll see where this comes into play on Wednesday, for sure. All right, now, again, you may ask, why are we talking about these? Our sole motivation in this chapter for talking about matrices is that so we can solve larger systems of equations. Okay? That is our entire purpose here. So, what I want to do first is play around with, hey, if you're given a system of equations, how do you write that in matrix form? And similarly, if you're in matrix form, how do you write that back into a system of equations? Okay? Because you're going to be given a system of equations, and you're going to have to enter that in matrix form into your calculator. So, let's just play with going back and forth for a little bit. Again, none of this is extremely difficult, but it's just stuff that you need to be shown so that you know the steps with which to proceed. Okay? And don't worry, there's more really cute examples coming up, a lot cuter than just the 2 by 2 matrix, I assure you. So, let us do this. Suppose I have the following system, and what I want us to do for these next 2 examples is the following. We want to write the matrix corresponding to the system of equations. And we'll do a couple examples here. Okay? Do you guys remember the term coefficients? Okay? If you don't, your coefficient is the number in front of your variable. So for example, if you have 5x squared, your coefficient is 5. All right? Coefficients are the key here. Now, the first way we're going to write matrices right now is called an augmented system. You don't have to worry about that term whatsoever. We're going to tweak it a little bit soon, but let's at least start here. So suppose I have this system. 3x plus 7y minus 8z is 5. Then I have x plus 3z is negative 2, and 4x minus 3y is 7. First off, you guys, you can always tell my 2's from my z's because I crossed my z's. All right. So, remember how at the end of class Friday we had set up that word problem before I gave you that extra credit question? Yeah. Okay? So, you saw that we got a system of 3 equations and 3 unknowns, somewhat like this. Okay? So, what we want to do is write this as a matrix. I will tell you for your equal sign, at this point, you just put a vertical line. Okay? Now, what you do is you put the coefficients in order. You want x's, then y's, then z's, and then what they're equal to. So will you guys grant me that my first row is 3, 7, negative 8, and then 5? Do you see how I got that? The numbers in front. Don't forget negatives. They're crucial. All right. What's the coefficient of my x in my second row? 1. Do I have a y? No. So what do we put? 0. Gotta put a 0. Okay. Then don't I have 3 and then negative 2? You with me here? What does my bottom row become? 4, negative 3, 0, and 7. How's that? A thrill a second, huh? All right, let's do one more of these. What if I have 2y, minus 3z is 5, 3x plus 2y equals 0, and x minus y plus 2z is 4. Okay. Guys, ready? Can you tell me what my first row should look like? Good, 0, because there's no x there. Then what? 2, then negative 3, and that equals 5. Are there any questions how we got that? What's my next row? 3, 2, 0, 0. Last but not least, what do I get for my bottom row? 1, negative 1, 2, and 4. Any questions on this guy? Okay, now what we're going to do is go the other way. I promise you my second example is cuter than my first example. But now what I want us to do is write a system of equations corresponding to the given matrix. And suppose I have this. 0, 3, 2, 4, 1, negative 1, negative 2, negative 3, and 4, 0, 3, 2. Now, someone asked, do we have to use X, Y, and Z? No, you can use whatever letters you want, but typically that's what we use is X, Y, and Z. So then, what does my first row of my matrix become in terms of equation form? Good. 3y plus 2z is 4. If you put 0x, are you wrong? No, it's just pointless. What does my next row become? X minus y minus 2z is negative 3. And last but not least, 4x plus 3z is 2. Guys, with me there? Okay, if you have questions, don't be shy. Let's do one more of these, okay? ready? This is a very intentional example. What does my first row become? X equals 4. What does my second row become? Y equals 18. What does my bottom row become? Z equals 5. Oh my goodness! Do you guys see how when our matrix is of the form where we have ones along our diagonal and zeros everywhere else, we can just read off our solutions? Isn't that cool? It is cool. Trust me. So, one thing that I want to tell you is if you were using that Gauss-Jordan elimination method, what you would be doing in order to solve a matrix is you would take a matrix, say that looks like this, and do all sorts of what we call elementary row operations and transform it to a matrix that looks like this. Because once you have a matrix in this form, do you guys see how you can read off all of your solutions? Now, you might wonder, what are elementary row operations? Well, essentially, and you don't need to write this down because it's nothing we're going to be doing. We're going to let our calculator do these things for us. But you're allowed to switch rows. You're allowed to multiply rows by numbers and add them to other rows and that sort of thing. Okay? But when you are doing it by hand with the Gauss-Jordan elimination method, your goal is precisely to take a yucky-looking matrix and put it in this form. Precisely as you picked up right away, you can just read off your answers. Isn't that cool? Okay, now, one aside that I would like to make, okay? The aside that I would like to make, and this is nothing that you need to stress out about because I'm not going to ask you to solve a matrix that doesn't have a solution. But do you guys remember how in class last time we'd solve a system of equations and we just had like 2 equations and 2 unknowns, and we got something nonsensical like 0 equals 7 or something like that, and we saw that there was no solution because they were parallel lines. Okay? You might wonder if you are in matrix form, and again, this won't happen to you, but this is in your book in case you read it. How do you know if you have no solution when you're dealing with a matrix? Well, you can have something like 1, 0, 0, say 4, 0, 1, 0, 3, and then 0, 0, 0, say 2. This is a situation where there would be no solution. Now, you're not going to say that they're parallel lines because this is actually a 3 values, different coordinate system. It's a 3-dimensional system. Okay? But do you see how with this bottom row, we got 0 equals 2, and how we knew when we got a nonsensical statement that we would have no solution? The same thing holds here. In a similar manner, if you have something like this, do you see how the bottom row gives us 0 equals 0? Okay. In situations like that, you may remember from last week, that told us that we have infinitely many solutions. That same thing will still hold here. Yes?
Does the top line only apply to that last value, or does it apply to the entire
That
matrix?
means that the system as it stands, there is no solution. There's no, in other words, for whatever we originally started with, there's no values of x, y, and z that you can plug in all 3 equations and get equality. Does that make sense? It's a lovely question. All right, so just to keep us further motivated with this, I thought we would do another setup, a word problem. Remember how I told you these things would keep creeping upon us? Yes? We will, but we don't know how to solve it yet. Yeah, we won't know that till like Wednesday or Friday. It's a long time to stay awake, isn't it? Okay, so what I would like to do is just another example of setting up a word problem. We did this because it was covered section 2.1. But as I mentioned to you guys, this stuff is in chapter 2 and in chapter 3, and I want to give you guys as much practice along the way. Okay? So, the one that I'm going to be looking at, in case you have your book, is number 78 in section 2.2. And this, if you don't have your book, don't worry, I will write down all of the relevant information here. Okay? This is called production schedule. It says a manufacturer of women's blouses, right? Who calls them blouses that much anymore? Anyway. Makes 3 types of blouses: sleeveless, short sleeve, and long sleeve. The time in minutes required by each department to produce a dozen blouses of each type is shown in the following table. Here's our table. So we have 3 departments. We have a cutting department, we have a sewing department, and we have a packaging department. And we have no sleeve, short sleeve, and long sleeves. And here are our values. Again, this is in your book, but I don't assume everybody brings their book. In other words, okay, they're given in terms of dozens of blouses, okay? We can just think of that as the units. It's not like that 12 really matters. But what they're saying is it takes 9 minutes in the cutting department for that group of sleeveless blouses, okay? It takes 28 minutes in the sewing department for those long sleeve blouses. You guys with me? Okay. Now, it says the cutting, sewing, and packaging department have a limited number of hours available. That makes sense. And in fact, the cutting has 80 work hours available. The sewing department has 160 work hours available. And the packaging department has a total of 48 hours available. Now, there's one little trick going on in this problem that I won't do to you. The units are slightly different. The units in the table are minutes, and here they're hours. I assure you guys, I will keep your units consistent. Okay? So, what the question then asks is the following. What we want to know is how many of each type of shirt can be made if all hours are used. In other words, we want to obviously use all of the work hours we have available. And so we want to know, given those limitations, how many of each type of blouses can we make? Now, maybe you could care less about blouses, but the point is if you have a company and you make different products, they take different times in different departments, it's not an unreasonable question to ask how many can you make given your limitations in your hours in each department. Okay? So, the way I will word these things always is to walk you through things. Part A, and this should be the way you always do work problems in life no matter what, but you should always define your variables. Okay? The first thing that we do. Now, you may or may not remember this from class last time, which is why I want to go through it very carefully. In order to define your variables, you always go to the question that is being asked. Literally, I go to my question. How many of each type of shirt? Isn't that what we're looking for? So, again, due to my my lack of originality, I'll use X, Y, and Z. I'll let X be the number of groups, because they were given in dozens, of no sleeve shirts. I'll let Y be the number of short sleeve shirts, or the packet of them. And then finally, we'll let Z be the number of groups of our long sleeve shirts. Does that make sense to everybody? Isn't that precisely what we're looking for? Again, you always want to indicate that you're talking about a quantity. You with me there? Okay, so again, in order to define your variables, you go to the question. Scoot this over. Okay, now, how do you set up your system? Because that is our next goal. Here's going to be another unsolved system for now. Okay, well, in order to set up your system, what you do is you look at your limitations. Aren't our limitations our work hours available? Yes. In my cutting department, what do I have? I have 80, right? I have 80 hours available. But remember, I'm going to be putting something, but let's just write these. And in my sewing, I got 160, and in my packaging, I have 48. Now, remember, I told you I wouldn't mess with you on this, but remember how these numbers are given in terms of minutes? You can't have one unit on one side of an equation and another unit on the other side. So the easiest way to convert all these guys to minutes is just multiply each of these guys by 6. Okay? I trust you guys can do that. You all agree that's how you change from hours to minutes? Okay. So, yes, we have essentially 4,800 minutes available in our cutting department. So let's talk about the time each batch of shirts takes. Well, for a batch of sleeveless shirts, how long do they take? 9 minutes. So isn't the total amount of time we spend cutting those shirts equal to 9x? Right? 9 minutes per batch times the number of batches. Okay? What's the total amount of time we spend with our short sleeve shirts? 12 Y. Right? It's 12 minutes per batch times the number of batches. And then don't I have plus 15Z? Guys with me there? Do you see how this corresponds to that nitrogen, phosphate, potassium example we did last time? All right, now let's talk about our sewing department. How much total time do we spend in our sewing for a batch of no sleeve shirts? 22 minutes per batch times the number of batches, so 22x. What's next? 24y plus 28z. All right, someone now tell me, what does my packaging equation look like? 6x plus 8y plus 8z. Don't worry, we'll keep practicing these. I like to throw in word problems, though. Are you guys okay here? Awesome. All righty. So, what I would like to do now is the following. I just want to get going in 2.4. So what I've done now is 2.2, 2.3. You guys will see you don't have many homework assignments, many homework problems for a lot of these. You want to read the instructions on my syllabus, though, because for a lot of them I say set up and don't solve. And then later on I'll have you go back and solve. Okay? So, what I want to say to you with 2.4 is here we're dealing with matrix addition and subtraction. Wednesday, first thing, I'm going to bring in some algebra for us to play with, okay, involving these. But it turns out that you can add or subtract two matrices if they are the same size. And you know, not everything in life turns out to be the way we would like it to be. But in terms of matrix addition and subtraction, things actually work out pretty nicely. Okay? The way you add or subtract two matrices is you literally just add or subtract the corresponding entries. It turns out that neither of these things are true for matrix multiplication. Things get very funky with matrix multiplication. We'll talk about that Wednesday. All right, so for example, what if I want to add these guys or subtract these guys? Let's see what we got. How about 6, 3, 8, 4, 5, 6, minus 3, negative 2, negative 1, and 0, negative 5, negative 7. Let's throw in a couple negatives here. There we go. Oh no, I don't want the negative there. I'll put it in here. I have this example and two more, and then we're good for today. Do you guys agree that I can subtract these two matrices? They're the same size, life works. Why do they have to be the same size? Because the way you add and subtract matrices is you add and subtract the corresponding entries. But if one guy's bigger than the other guy, he has nobody to hang out with. Okay, everybody needs a partner, essentially. So, in this case, we're going to be subtracting because we have a subtraction sign. Key thing to remember, isn't minus a negative plus a positive? Okay, so what is negative 6 minus 3? Negative 9. Next term, what is 3 minus a negative 2? A positive 5. You guys with me? What is 8 minus a negative 1? That's plus a positive, so it's 9. What is 4 minus 0? 4. What is 5 minus a negative 5? 10. Right? Minus a negative is plus a positive. Last but not least, what is negative 6 minus a negative 7? 1. Oh boy. Isn't this exciting? Okay, let me ask you guys what you would want to do if I put you in this situation. Okay, what if I had a negative 2 in front of this matrix? Negative 1, 3, 7, negative 4. What would you want to do with that negative 2 in front of your matrix? Wouldn't you want to multiply every term by that negative 2? Oh my God, totally, right? You're thinking, this is just like distributive property. Yeah, okay? When there's a number in front of your matrix, he's called a scalar, if anybody really cares. The point is, exactly what you want to do is exactly what you get to do. Isn't that awesome? So, what do you get if you take negative 2 times this matrix? 2. Negative 6. Negative 14 and 8. Are you all thrilled? We are building up to something, I promise. But here's our last example for the day. Oh, I'm about out of overhead, so timing works. Okay, what if I have this guy? Order of operations say multiplication before addition or subtraction. Do you agree? Okay. Now, I have 2 times this matrix. Do you all agree I would take each entry and multiply it by 2? Do you agree I would have 2, -4, 4, -2, 6, and 0? Questions this far? All right, I am going to pause. Okay? The reason why is with this next step, you can look at it one of 2 ways. They're equivalent, but let me show you. Do you agree I'm subtracting 3 times this matrix? So what I could do is put a minus sign and then multiply each of these guys by 3. Do you all see that? Okay. Do you also agree that I could say, well, this is the same as plus -3 times that matrix? Do you all see that? Okay? Right? Minus, plus, and negative, they're equivalent. Okay? You could keep the minus sign and distribute your 3 throughout this matrix. But what I'm going to do is I'm going to make a plus sign and multiply everybody through by -3. There's a reason for it. It's next class. Something else will be a little easier if you look at it this way. It's not wrong if you want to keep a minus sign and multiply by 3. The key thing is a lot of people forget minus and negative is plus and positive, and next time I'm going to be having more than one term in these guys. So if I multiply everybody through by -3, do you agree I have -6, -9, -3, 6, -6, and -12? Assuming I multiplied correctly. You guys with me this far? So, let's add them up. What is 2 and -6? -4. What's -4 and -9? -13. What's 4 and -3? 1. What's -2 and 6? 4. What's 6 and -6? I just love that. And what's 0 and -12? -12. You guys with me? All right. So, if you want to start doing some homework,